factoring you've done to this point, factoring polynomials. Remember that factoring is just the reverse of multiplying. The first section you learned to take polynomials and multiply them out to get a single polynomial as your answer. Now you're working backwards, right? You're factoring, you're breaking them apart. Two things you got to look at here. We're looking at factoring special polynomials here. Special polynomials. You thought that all polynomials were special in their own way, but they're not. There's some that are more special than others. Really what we did before was factoring special polynomials. I guess these are even more special. We've done this kind of factoring. We have started with the factoring out the greatest common factor, GCF factoring. That's the kind of factoring where you take a polynomial and make it into a single term times stuff that's left in the brackets to put it in really everyday terms. Then we did factoring. That was section 5.2. Okay. Then we factored what are called trinomials in 5.3. If we flip back to that section for a second here, so if we have a look back at this section, and let's scroll right back to the beginning. This is when you had polynomials that look like this: something x squared, something x, some number on the end, right? Or there could have been a number at the beginning. The way I had you start that was to take these things and multiply them out so that then we can look at how do we go backwards, right? That was the strategy here. The first page wasn't factoring, it was multiplying, and then we're look at the pattern and work backwards. These were all special because the two things I asked you to multiply out were two binomials, two brackets, and they were two binomials where they started with x and had a number second. And we looked at sometimes what happens if both of them are negative, what happens if they're both positive, what happens if they're opposite signs. The ones we're going to work with now are even more special than that. So we're going to do two things, and I'll flip back and forth here and you can compare. If you look at this page and you look at the pairs of binomials here that we're multiplying out, and then we look at this page and we look at the binomials that I'm asking you to multiply out, you can think to yourself, you don't have to say it out loud now, but you can think to yourself, what's so special about all these ones? Because again, this is going to be, you're going to multiply them out, but then we're going to see what's the pattern that we can use to go backwards, right? Because factoring is just going backwards. So at first you're multiplying them out, and then it says, what's the pattern? You're looking for a pattern in these being all these are special in a certain way. And that's going to give you one kind of special polynomial. So the thing that results here is going to be called a difference of squares. You should think about why is it called a difference of squares. We can look later, or you can think about later how those pictures might lend themselves to this, or it might represent that. There's a whole bunch here to work with and factor. This is going to become your favorite kind of polynomial factoring because you'll find it to be the easiest one once you know what you're doing. All right? Second kind of factoring is called perfect square trinomials. This is a perfect square trinomial. And you can look at, again, here I'm asking you to multiply it out, expand and simplify it. You can look and compare this to the first page in this section and say, how is this the same and different from the first page? Right? How are those things that multiply out, how are they the same and how are they different than those ones? And how are they the same and different than just the basic old trinomials that weren't that special, right? So you got to look for some comparisons and look for some patterns. Factoring here, being good at factoring is looking for patterns and not trying to memorize stuff, right? Looking for patterns as you work on this. So I want you to try this first by doing this and think about, we'll look at it in a few minutes here and talk about what you've hopefully discovered as you multiply this out, okay? So discuss with someone how these compare with the second part of this and how they compare with last time. Okay, I'm going to pause this for a few minutes while you do that. The pattern, maybe, hopefully you've noticed it. Hopefully you did some of each, some of the part A and some of the part B. First of all, what is different about this, or what is so special about this compared to in the section before it? In this section, what's the first significant difference? What's so special about 5.4 compared to all the sets of brackets that are here? What's the difference? What makes all these special? You can do this if you've looked and you've seen. You must have noticed this, right? Look at all these sets of brackets. And then look at all these. What's so significant about this? Each pair here, what's true about each pair I've given you here? They each have a variable and a constant. That one has not just starting with x. What's true about each pair of brackets here? What's true? If you look at this bracket and you look at this bracket, what's true about every single one of these pairs here? Why does nobody want to say anything? You're afraid to speak? All of these, each of these things here, it's just, x plus 6, x plus 5, it's just whatever numbers I happen to put in there. Okay, whatever numbers, right? 10 and a 3, 6 and 5, whatever. What about 5.4? What's true about every single pair here? You got to tell me you noticed this. You must have noticed this if you've done this. You can't tell me you started multiplying these out and didn't notice this. You notice? Please tell me you noticed that each of these pairs of brackets was the same except for one of them has a plus, one of them has a minus. You didn't notice that? Okay, I'm going to assume that you just don't want to say anything right now, but that you noticed that. Let's do one of them the long way, and then I'll tell you why I want you to do it without a step in between here. If you're doing the first one the long way here, actually, it doesn't matter which one, but the first one here. If you're multiplying that out, and you do x times x, you get an x squared. And then you also need to do, like, the first term comes from the first terms in each brackets. We know that already from factoring before, right? First term comes from the first terms in each bracket. The last two terms in each bracket are going to give you a minus 4. So you're going to have x squared and you're going to have a minus 4. What about the other two terms? The inside and the outside terms. The outside terms here give you like this, x times minus 2. What does that give you? Minus 2x. What about the inside here? What about the inside terms? Plus 2 times x gives you plus 2x. What's true about those two things? They cancel each other. What do they add up to? They add up to 0, right? The outside and the inside terms are going to cancel each other out. What's the simplest way to write that whole big thing? X squared minus 4. That's all it's going to be. If you notice that the brackets are identical, other than the plus minus, one's plus, one's minus, the middle terms are going to cancel out. All right? Whether you did it with algebra tiles, whether you did it with a rectangle, whatever model you're using, this is called the difference of squares. Why do you think it's called the difference of squares? What does the word difference mean in math? Subtraction, right? Subtraction of what? Of squares. What do you talk about when you talk about squares here? A number that's a square, a perfect square, is 4 a perfect square? Yes, it is, right? 9, is that a perfect square? Is 10 a perfect square? 10 is not a perfect square, right? 4 is a perfect square, 1's a perfect square, 9's a perfect square. What's another perfect square? 16, 25. Those kind of numbers are perfect squares because you can make, there's something squared. They're a whole number squared. 5 squared, 4 squared. This is a difference of two squares because it's the difference of two squares, right? It's called a difference of squares because it's a difference of squares. It's subtracting two perfect squares. X squared minus 4, both of those things. X squared is a perfect square because it's x times x. Oops, got to rewrite it now. I messed it up. X squared is a perfect square because it's x times x. 4 is a perfect square because it's 2 times 2. Any of these things is going to give you the result is going to be a difference of squares. The pattern here now we want to know is, how do we go backwards from this if we have a difference of squares? So if somebody says you have a squared minus b squared, what can we factor that as? We can factor it into two brackets, even though it's not a trinomial, even though it doesn't have three terms. How can we write it? What is it going to be? What is that going to be? A squared minus b squared, are each of those things perfect squares? A squared's a perfect square because what is it? A times A, right? B squared's a perfect square because what is it? It's B times B. If I want the middle term to cancel out, what has to be true about these two brackets I'm writing here? They have to be exactly the same except for one has to have a plus, one has to have a minus. Would the middle term cancel out if they both had a plus? No, it wouldn't, right? The only reason the middle term cancels out is because one ends up being positive, one ends up being negative. When you're looking at algebra tiles, this is what you're doing here, okay? When you multiply out something with algebra tiles, let's say we multiply out, I don't know. Let's say we multiply out x plus 3 times x minus 3. If you're multiplying out x plus 3 times x minus 3, if you put x and you put your plus 3 over here, so I've got x plus 3, and I'm going to put x minus 3. So I need this, I need to turn it, put it on the side, and I need minus 3, so I need 3 of these, right? Minus 3, 3 white ones. If I want to fill this in, what's the result of that? What's the result right here? X times x gives me x squared, plus 3 times x, what does that give me? 3x. I need 3 of these, right? 3 green ones, and they have to be this way so that I can fill them in here. And then, whoops, what am I going to, a little slow on the rotation here. One more. Whoops, not quite. What about this down here? What goes down here? Negative 3x. Okay, this is kind of slow, but that's okay. And what goes down here? What color are these ones? You have positive 3 times negative 3. Negative 9. Fortunately, I hope I can just grab them all that shape already. When you multiply out things, if you have a negative here, if you have you have to, the signs have to work. If you have a negative involved here, you're going to have the whole strip being negative. If I want to simplify this, this is written as x squared plus 3x minus 3x, right? X squared plus 3x minus 3x. If I write x squared plus 3x minus 3x and then minus 9, this adds to, what does that add to? It adds to 0, right? That's the same as this and this thing. These are 0 pairs. What do those add up to? I can make 0 pairs out of them, right? If you have those stuck together like that, that adds up to 0. And here's another 0 pair, right? This is a 0 pair. Doesn't give me the little rotation thing. Where is it? Come on. I'll rotate this one then. Never mind. There it is. Close enough. We'll fix it. And then third 0 pair here, right? You can get rid of all of those things. You can take away this 0 pair, that 0 pair. You can take away this 0 pair. And you can take away this 0 pair. These two things together are 0, even though they're not stuck together. What am I left with here? X squared minus 9, right? X squared minus 9. I have x squared minus 9. Now when we're going backwards, if somebody asks you to factor this, instead of taking away 0 pairs, what do you have to recognize in your head? You have to say, oh, that's one of those ones where you're going to have two terms that cancel out. If I want to factor this, it has to be something times itself because these have to be the same size here. It's not going to work if you make it so those are different sizes, right? You can't make this into x plus 9, x minus 1. Why can't you do that? Why can't you make it x plus 9, x minus 1? Are the two terms going to cancel out if you did that? It doesn't work, right? It's not going to work. That'd be the same as lining up the ones here. It'd be the same as lining these things up so that they didn't work, right? So that was like this. Is that going to allow you to have middle terms that cancel if they're lined up like that? as in if you have a 1 over here, and you have a bunch of them over here, you have 9 up here, you can't have this so that it looks like this, right? That's not going to work because are these going to fill in? Are these going to cancel out? When they're different? Not going to cancel out. You got to have it so it cancels out. You got to arrange it so it's 2 squares here, the difference of 2 squares. Factoring is going backwards here. What is this one going to factor to? X squared minus 81. You got to recognize it's a difference of squares. You're going to think that this is the greatest kind of factoring here because you can just do that. Double check that it works. There's a few harder ones down here where there's all kinds of crazy letters, but it's still, the 2 brackets have to be identical, except for the plus and minus. That's the first kind of special trinomial. Okay, the first kind of special trinomial. Can you get working on that? I'm going to stop you in about 10 minutes and talk about the second one. Make sure you've gotten up to the second one in trying these. Okay? Try multiplying out some of these and look for the pattern. Don't let yourself get off task. Okay?